Welcome to the first of our Calculus 3 series of videos. And in this unit, we're going to discuss vectors and the geometry of space. So the first video talks about the three-dimensional coordinate systems. So in order to describe the location of a point in our familiar rectangular, or sometimes called Cartesian coordinate system, we need an ordered pair, right? X comma y. And two coordinates are required in this two-dimensional system. And when you're in a two-dimensional system, an equation relating the values of x and y has a graph that is a curve in the plane. Now, at this point in our calculus career, we want to move beyond two-dimensional systems and into three dimensions. And so a point in 3 space is represented by an ordered triple here, x, y, z. And as you would expect, a location in 3 dimensions requires 3 coordinates in order to uniquely determine where it is. And as we will see, an equation relating x, y, and z will have a graph that is referred to as a surface in space. Now, when you're plotting a point in 3 dimensions, you have to first set up the coordinate system. And just like in 2 dimensions, the axes are number lines intersecting at 0, which is the origin, and they're all mutually perpendicular. So typically it's represented as follows. Notice that the positive x-axis runs towards you and the positive y-axis is towards the right. And in a right-hand rule system, which is the one that we use, the positive z-axis runs upward. So what do we mean by a right-hand rule system? So if you take the fingers of your right hand alongside the x-axis and then you curl those fingers towards the y-axis, your thumb points in the direction of the z-axis. So that's how you know the direction of positive orientation. Now, often we're going to refer to the coordinate planes. So for example, if we talk about the xy plane, that plane contains both the x and y axes, and it consists of all of the points for which z is equal to 0. So I'm going to list it out here. The xy plane, its equation is given by z equals 0, actually. And you could think of it like if you're standing in the room, that it's the floor. Well, what do I mean by that? It's basically this region here, right? The xy plane, and it extends forever. And it's basically our original 2 space, right? XY coordinate system. Now, if we talk about the XZ plane, its equation is given by y equals 0. And that would be all of the points where y is equal to 0 and x and z could be any value. So that's basically, let me draw xz plane is coming out towards us, and it goes into the board or into the wall, whatever you're looking at this video on. It extends in all directions. And then lastly, we can talk about the YZ plane. And that has the equation x equals 0. So all of the values where x equals 0 make up the YZ plane. And if you want to think of it as this back wall straight on towards us, okay? And of course, yes, it extends in this direction, that direction, up and down as well, okay? Just for some orientation. And in 2 dimensions, the x and y axes split the plane into 4 quadrants. However, in 3 dimensions, that translates to having 8 octants. And pretty much the only one that we're going to refer to frequently is the first octant, and that's where all x, y, and z coordinates are positive. Okay, so all the positive axes determine the first octant. Now, if we're going to plot points in 3 dimensions, it often requires some sketching aids in order to provide us with proper perspective. So here's where you have to just be careful with how you label and scale your axes to make sure that your points line up properly. So we're going to plot the points 3, 2, 5 and 4, -2, -1 on the axes below. I always begin by labeling my axes. So here's the positive x-axis, y-axis, z-axis. I'll label this one too while I'm at it. And notice when I scale my axis, I'm going to scale the little tick marks parallel to one of the other axes. So notice, like along the x-axis, these tick marks here are going to be parallel to the y-axis, 1, 2, 3. And then here on the y-axis, I'm going to draw my little tick marks parallel to the x-axis best I can. And then z-axis, they're going to be parallel to the y-axis. So here, the first point I want to plot is 3, 2, 5, right? Okay, So what that means is I need to move 3 units in the x direction, then 2 units in the y direction, and then finally 5 units in the z direction. So the first part, 3, 2, that's not going to be too hard, right? So if I go 3 units in the x direction, 2 units in the y direction, that's going to take me here. But how do I use the proper perspective to show that I need to go up 5 units in the z direction? Well, here's 5 units up in the z direction, right? This was 3, this was 2. And this distance here needs to match the distance that I move upward from 3 to 0. Okay, so just use some perspective. I'm going to copy this so I match it perfectly here. And then that means the point right here is 3, 2, 5. That's our final point. Okay, so those two distances must match. Now, what about the next point here? We have 4, -2, -1. Okay, so same thing. I'm going to go 4 units in the x direction. So 1, 2, 3, 4. Now I need to go -2 units in the y direction. So I'm going to extend the y-axis a wee bit and then go -2 units. -2. Okay, so then I can see here. Here's 4, -2, 0, right? All right, now I need to move down 1 unit in the z direction since z is equal to -1. So I'm going to extend that z-axis just a little bit. Here's -1. And then that distance here, so this time I'll just do it in red so it stands out. That's the distance I need to move down from 4, -2, 0. Okay, so I'm going to erase this so it doesn't get too messy. We all know where it's at. And then I'm going to copy this distance. Whoop. It's not liking it. So we're going to eyeball it because I'm good at eyeballing. Okay, so it's about this much. And so this is where our final point for -2, -1 would be. 4, -2, -1. All right, good. Now we're going to practice sketching some graphs here, and we're going to do their equivalent in 2 space as well as in 3 space. Okay, so first example, say we're graphing x equals 2. Well, in a 2-dimensional coordinate system in 2D, here's my xy plane. Well, what does this equation represent the graph of? It's just the graph of a vertical line, right? Let's put one over here because I know I'm going to need it in a hot second. Okay, and so it's just the graph of a vertical line. All the x values are 2. And so I'm just going to graph that line, make sure everything's labeled nicely, and don't forget your arrows. Okay, now in 3 space, what would the equivalent be? Or in 3D? Okay. Well, you're going to have here's my z-axis, here's the x-axis, here's the y-axis, okay? It's all of the values where x equals 2, okay, fine. So come along here to where x equals 2. That's basically the line that we drew in 2 space, right? You could imagine if you were standing up on the positive z-axis looking down at it, you'd have the same graph. But also, it includes any value of z. So it's going to go up and down forever this way. And what we have is actually a plane. Okay. So this is the equation of a plane. All right. Now, moving on to our next example, if we were to graph y equals 3 in 2D, that would be a horizontal line passing through the y-axis at 0, 3, and it contains all points whose y-coordinate is equal to 3. Okay, now what would be the equivalent graph in 3 space? What do you think? Yes, we're going to get another plane. Okay, it's just going to look a little bit different. So here's my z-axis. Here's the x-axis. Here's the y-axis. Okay, so to start, you draw your line, y equals 3. So 1, 2, 3. And that line's going to be parallel to the x-axis, right? That's y equals 3. Okay, and so since the equation is only y equals 3, think of it this way. There's no restrictions on x, so x can take on any value. Well, that's exactly what I've drawn there. You know, it doesn't look super parallel. Let's fix that. Let's make it perfect. We have no excuses. Okay. And then also z can take on any value, so it's going to extend forever up and down this way. Let me extend it a bit further so you don't think that it ends there. Beautiful. Okay, so it's a plane. Think of it like it's a piece of paper, but it extends forever, right? Here we go. Here's another plane. All right, looks nice. Next example, y is equal to x. Okay, so in 2-space, in 2D, we know this is a line whose slope is 1. Y-intercept is 0, so it crosses through the origin. And you should also know that it makes a 45-degree angle with the positive x-axis, right? So here's y equals x. And I'll indicate this is 45 degrees. Okay, well, in 3-space, what would it look like? Here we go. In 3D, I'll draw my z-axis a little longer. Yeah, let's go for it. And then here's the x-axis. Here's the y-axis. Here's the z-axis. Okay, so x equaling y, that's going to come this way, right? This is the equivalent to what was in quadrant 1. And then that's going away from us. That's the rest of the line that I have in the 2D graph. And then again, z can take on any value. So you're just going to extend parallel to the z-axis to create some perspective. And then here's our plane. All right, and then I'm going to just shade it in. I suppose that's a good color. There we go. So there's our plane. All right. Looks very nice. Now our last example here, xy is equal to 0. We're only going to graph this in 3D, okay? So let's think about what's going on. Xy, x times y is equal to 0. Now, if x is equal to 0, then this is going to be equivalent to graphing the yz plane. And similarly, and I'm just coming up with this idea because of the zero product property. If x times y is 0, then either x is 0 or y is 0. So if y is equal to 0, then that means my graph is going to be the xz plane. So basically graphing x times y is equal to 0 is equivalent to graphing both the yz plane and the xz plane. So here we go. We're just going to graph and shade in both of those planes. So x-axis, z, y. So first let's graph the yz plane. That's where x is 0. So yz plane is all of this back here, and then I could even extend it past here, but it's going to get a little messy. Okay, and then if y is 0, then I'm going to graph the xz plane. So that's this portion here, right? And it extends back beyond there too. You could include negative x values. I'm not going to make a hot mess of this, but you get the idea. Okay. Now let's look at a few more interesting graphs. We have y is equal to x squared. So if you'll recall in 2D, what is this the graph of? Y equals x squared. Hopefully you know. It's your good friend the parabola, right? Okay, so it's a parabola whose vertex is at 0, 0. It opens upward. I'm just going to put a rough little sketch there. Okay, so what does this equate to in 3-space? So what you're going to do is draw the same graph in the xy plane, okay? And then since z is missing, you're just going to project the graph parallel to the z-axis. I'll show you exactly what I mean. So here's the z-axis. Here's the x-axis, here's the y-axis. Okay, if you want to get really particular, you can start like scaling things and plotting specific points. I mean, we can do that if we want. So here's 1, 2, 1, 2, 3, 4, negative 1, negative 2. So, okay, if this is a parabola, it's going to go through 0, 0, 1, 1, negative 1, 1, and then 2, 4, negative 2, 4. So here's our graph from earlier, right? Just in the XY plane. And then what you need to do is project this graph parallel to the z-axis. So the best way to do it is you just pick some arbitrary distance, okay? Say I'm gonna project it maybe this much, okay? And then I'm just gonna copy that point, that distance, and attach it at various points on the graph. Let me just do it straight from the XY plane. So say I'm gonna extend from each of the points I plotted this arbitrary distance. I'm gonna be consistent now about how much. Let me copy it. That way I know I'm consistent. Okay. Copy. So we're gonna paste one here. And then I'm gonna paste another one here at this point. Then I'm gonna paste another one. Just keep going. At all of the points. Let's do one more. And then, voila, when you connect them, you should get the graph projected in the z-axis, along the z-axis. And then here I can shade in so you see the parabola. That part's towards us, the other part's away from us. Okay? What about x squared plus z squared equals 16? Okay, so just think to yourself, what variable is missing? Y is missing, right? So first I'm just going to draw this in the xz plane, and then I'm going to project my graph parallel to the y-axis. So let's go for it. So in the xz plane, what is this going to be the graph of? Well, it's a circle, right, with radius 4. So yeah, you know what? Let's extend this a little bit more. X, Z, and then we're going to project it along the y-axis. Okay, radius is 4, so I'll say that's 4. I'm scaling by 2's. So we're going to start off by just graphing that circle in the XZ plane. You know what? It doesn't do perspective, so I'm just going to have to do this by hand. Okay, and then you're going to pick some arbitrary distance and project that. Let's say we'll add it onto each of these 4 points here, okay, in the y direction. So say the distance I'm going to pick is maybe this much, okay. I'm going to copy it, paste it a bunch of times onto each of these points. And then if you're just drawing it by hand, no problem, that's how I used to do it. So you're just going to be consistent with however much of a distance you decide to add on. Okay, and then we'll get rid of this guy here. And then now I'll connect them all. So we'll have these points here. Okay, not bad, not bad. And then we can shade in. This is the outer surface towards us, right? Just to add a little perspective. Okay, looks good. Now we can also graph three-dimensional inequalities. So say we were to graph x is less than or equal to y, okay? In 2 space, let's think about how we would do that. So first you would just graph the equality, right? The boundary of this inequality, which would be y equals x. And since it's inclusive, then I'm going to graph a solid line at y equals x. So this is in 2 space. Here's y equals x. And then the inequality is telling me I need to also include all of the values for which x is less than or equal to y. So that would be all of the points that are above the line, right? Now, how would this translate in 3 space, in 3D? Okay, well, first you begin by graphing the boundary. So the boundary would just be the equation y equals x. Well, we graphed that previously, didn't we? We graphed the line, or the plane y equals x in 3 space. Y, z, x. So remember, x equals y came out towards us this way, went back that away, and then it made a plane. We drew pieces parallel to the z-axis. Here's this plane. Okay. Beautiful. And then think about the fact, okay, now the inequality is telling me I need all values where y is greater than or equal to x. Well, just like we shaded above the line, this time the equivalent in 3 space would be all of the points that are behind the plane. So your entire graph includes all of the points that are on, right, since it's inclusive, and behind the plane. And that's the best way to express your answer. Don't get carried away with doing lots of sloppy shading. Just draw some arrows to indicate, and then if you need to add some words to describe the region, that's totally appropriate. Okay, now let's look at some other 2-dimensional, 3-dimensional analogs. So first we have the distance formula, right, between 2 points, x1, y1, and x2, y2. You'll recall the distance formula is given by the square root of x2 minus x1 squared plus y2 minus y1 squared. And hopefully your instructor has shown you at some point in your math career the derivation of it. So to get the distance formula, you basically make a right triangle connecting the points x1, y1 and x2, y2. And the direct distance between those 2 points, that's the hypotenuse of the right triangle. The base here is one of the legs, and then here's the height. And the height is given by y2 minus y1, right? The difference in the x coordinates. And the base here is given by x2 minus x1. So if you apply the Pythagorean theorem, then you can get the distance. Now let's see how this can be extended to 3 dimensions. If I were to not show you any derivation, any background, and I just said, hey, guess what the distance formula is in 3 space, what would you guess it to be? Well, most likely you're just going to say, let's slap on a z2 minus z1 squared, and you would be correct. So you have distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. All right, but now let's see how we would come up with this exactly. So what we're going to do is look at a similar situation, but this time we're working with points in 3 space. So to start off, we're going to make a rectangular solid instead of a triangle, okay? And I'm going to label one of the vertices x1, y1, z1, and the other one x2, y2, z2, okay? And I'm going to label them in such a way that I know all of the coordinates are distinct. So the x coordinates, y coordinates, and z coordinates will be different. So in order to do that, I'm going to call this point back here x1, y1, z1, and then this opposite vertex over here, x2, y2, z2. So I know that the x coordinates are different, the y coordinates are different, and the z coordinates are different. Okay, so how would I go about figuring out the distance between these 2 points? So the distance would be right here. That's the distance. Okay, well, first what you're going to do is just look at the base of this rectangular solid. And I know the coordinate of this lower vertex here is x2, y2, z1, right? It has the same z coordinate as the other point there, which means this distance here of this side is going to be y2 minus y1. And this distance here is going to be x2 minus x1. So I can actually go ahead and figure out the length of this diagonal here using the distance formula for 2 space, right? Since we have a little right triangle going on. And so this distance here is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, now that we have that distance, I want you to look at a new right triangle, and I'm going to highlight it here. Okay, so focus on that triangle. It's a right triangle, yes? Do you agree? Bam. It's a right triangle. Now I know the height here. The height is going to be z2 minus z1, right? And I have the base of that triangle. So let's use the distance formula now to find this distance here. So d squared is going to equal, well, I have the base there, which is already this quantity, and I'm going to square it. So I have square root of x2 minus x1 squared plus y2 minus y1 squared, and this gets squared, plus, and then I have this side here squared, so I have z2 minus z1 squared. And then now you can see, okay, this is going to cancel with my square root, and then if I want the distance by itself, then it's going to be the square root of what I have up above, which we all guessed to begin with, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay, very nice. Now, just as the two-dimensional formula, distance formula led directly to the equation of a circle, if you'll remember, the three-dimensional distance formula leads directly to the equation of a sphere. So the equation of a circle, just if you'll recall, whose center is at h comma k with radius r, is given by x minus h squared plus y minus k squared equals r squared. Similarly, the equation of a sphere is given by x minus h squared plus y minus k squared plus z minus l squared equals r squared. And in this case, the center we say is at HKL. All right, and the radius is r. So here, just look at a straightforward example. If you need to write the equation of a sphere with center negative 1, 2, 4, and the radius is 1/2, it would be x plus 1 squared plus y minus 2 squared plus z minus 4 squared equals 1/2 squared, which is 1/4. All right, very nice. Next example, find the center and radius of the sphere. 2x squared plus 2y squared plus 2z squared plus 4y minus 2z is 1. So in this case, we need to make sure that we complete the square for x, y, and z if necessary. And also I want to, before I begin doing that, divide everything by 2 since I want the coefficients of all of my quadratic terms to be 1. So I'm going to have here x squared plus y squared plus z squared plus 2y minus z equals 1/2. And then now I'm going to begin completing the square where appropriate. So x has no linear term, so I don't need to complete the square for that. So I'm just going to have x squared plus, and then notice here I have y squared plus 2y plus, I'm going to need to add something to complete the square there, plus z squared minus z plus, going to need to add something to complete the square there, equals 1/2. And so for y squared plus 2y, I need to add a 1. Remember, I take the coefficient of the linear term, divide it by 2, and square it. And then I have to also add a 1 on the other side of the equation. And then for z squared minus z, I'm going to need to add 1/4, right? Taking negative 1, dividing by 2, and then squaring it. And I have to also add 1/4 over here. So now I'm left with the equation x squared plus y plus 1 squared plus z minus 1/2 squared is equal to, let's see, this is going to be 2/4 plus 4/4 plus 1/4 is 7/4. Beautiful. So let's box this, and then we'll list the center and the radius. So the center is at 0, negative 1, 1/2, And the radius, remember on the right hand side, it's r squared. So the radius is the square root of that. So we have rad 7 over 2. Very nice. Okay, last example, describe in words, so you don't have to graph it, the region represented by the following inequality. So we have x squared plus y squared plus z squared is greater than or equal to 1 and less than or equal to 25. So think about it this way. If you had x squared plus y squared plus z squared equaling 1, that's a sphere centered at the origin, right? Radius is 1. If you have 25 equaling x squared plus y squared plus z squared, again, that's a sphere centered at the origin whose radius is 5. So this inequality is telling me that basically I have all of the points on and between those two spheres centered at the origin with radii 1 and 5. So you could think of it, it's going to look like a sphere whose radius is 5, and then someone came and scooped out a sphere from the very middle of radius 1. But we just have to describe in words, we don't have to draw. So I'm just going to state, okay, it's all points that are on because, why? Because the inequalities are inclusive, right? So on and between spheres centered at the origin with radii 1 and 5. Okay, so try to visualize what it would look like. And that concludes the first video.